Hello everyone, welcome back to the channel EC TechNest. Today in the day 17 of the 100-day series of digital Verilog and design series, today we are going to speak about shift registers. Shift registers are essentially a chain of flip-flops, usually D flip-flop, that pass data bits from one to the next at every clock pulse. Think of them as a digital bucket brigade. What I mean to say here is shift registers hold the data for a very small amount of time and they change the way it is taken in and taken out. So we have different combinations of it. Let us see how it is. The four types are defined by the how the data enters and leaves the register. That's what I mentioned. CISO, serial in, serial out. CPO is serial in, parallel out. PISO is parallel in, serial out. Parallel in, parallel out. Here, what matters the most is the number of clock cycles it takes to perform this operation. Let us see each one of them. First, we have serial in and serial out. In a CISO, the output of the one flip-flop is connected to the input of the next. Here, this Q is connected to the input of this flip-flop 2. Then we have the output of flip-flop 2 connected to input of flip-flop 3. So in this way, the clock is connected to all the flip-flops. Now let us assume I want to send this data 1010 serially. So first 0 will go, or else let us consider we are sending from 1010, right? So we'll send 1 first, then this one will go to this one will go to here, and this one will go to 0, if that is the case. So what happens is first 0 will go here, here, here. Like by the time it finishes the fourth clock cycle, it will come to the last flip-flop. Then one would have gone, so it will come to the third flip-flop. So you need four clock cycles to put the data inside this first four flip-flop. Now you assume that you want to take the whatever is inside this flip-flop as output. You need four more clock cycles. That means first you will hold on to 0, then you will, 1 will come here, you will hold on to 1, then you will get 0, you will hold on to 0, then again 1 will come. So it will take another 4 cycles. So totally it will take first 4 clock pulses to get the data into the register and another 4 clock pulses to get it out. Let us see how we can write a Verilog code for CISO, that is serial in and serial out. You have three inputs, that is serial in, reset and clock, and your output is S0. For my convenience, I'll have a temporary variable that is temp, and it will be a 4-bit. I'll explain you why we need that. Always at positive edge of the clock or positive edge reset. What is this called as? We are using synchronous reset method here. If you haven't known what is this, you can watch our day 16 video to understand properly about synchronous and asynchronous reset. We'll begin this. If reset is high, or your output will be all in zeros. Else, what you will do is you will give the whatever is in this input to the temporary variable. What will happen is serial input and whatever is your variable from 0 to 2, that is in 3 bits, that will get transferred to this temporary variable, and what is our output is there, it will be temp3. So what happens is this s0, when we see the diagram here, if you have s0, this will be the last bit, right? So this will directly go to that, and the other 3 bits will sit here. So we'll get total of 4 bits that will get stored in the temporary variable. Yeah, you can see here. First bit 1 enters flip-flop 1, then whatever is in the flip-flop 0 will move to the flip-flop 1, then it will go to the flip-flop 2. Here it is a bit confused because I have numbered it as flip-flop 1 and I am saying here FF0. It means this is FF0, FF1, FF2, FF3. So in that way, this will keep on shifting. Here the delay formula is nothing but you have total time to recover data in 2 power n minus 1 clock cycles. So you are having 2 power This is totally 4 bits, right? So 2 fours are 8, 8 minus 1, 7 clock cycles. But you might be confused that we are telling 8 clock cycles, right? So it is because here when you hold the data at the 8th clock cycle, you'll get the complete output. So we are telling it requires 7 clock cycles, but it is actually 8. So we'll read about serial in parallel out. Here what happens is data is entered 1 bit at a time in series, but the output is in available in parallel. So what happens is you use where is this used? A serial to parallel converter. This is used for transferring data over a single wire. One thing is it generally saves space, and then it is easy to present it in parallel. This is helpful in communication devices. So let us see how to write the code for CPO. It is very similar to whatever we wrote for our CISO, but the only change will be here is the output here. We have parallel out. So directly whatever is there is in the temporary variable, it will comment it in this. So this is how it is going to work. All 4 bits will be available at once. Then this is the configuration for being a pin saver. You send data over one wire, that is your serial input, and it can be used to control many output like 8 LEDs simultaneously. How this works is data is shifted in serially exactly like the CISO. However, the output queue of every flip-flop is connected to an external pin. That means here you have a separate parallel output after every flip-flop. After n clock cycles, the entire binary word is sitting on the output. You do not need to shift it out to read it. You just read all the Q pins at once. They mean to say is when you put the data serially in, before going to the next flip-flop itself, one of the data will be already parallelly out. So it will be easy for you to read it. Next we have parallel in serial out. Here what happens is the data enters parallelly at once, and it takes 4 clock cycles for it to serially go out, or n clock cycles, because for 4 bits will require 4 clock cycles. If you have a 4-bit register, you need 1 cycle to load. Loading is giving the input, and 4 cycles to read the full message. So here it is totally 5 cycles. It is divided into 2 phases, that is loading phase and shifting phase. Loading phase will be your parallelly giving the input, and shifting phase will be reading the output. That means after shifting all the like whatever you have given the data in parallel, you need to shift it right to all the flip-flops. That is when this is used. Here one important mode we have, that is using shift. Consider your shift is uh, either 0 or 1, and this is your load line. So what this load line does will exactly tell you using this operation method. Consider your shift to be 0. So this shift is 0, and this load line is 1. Obviously if this is 0, this will become 1. So now your load line is active. That means this part of the AND gate has 0, right? This is connected here. So this becomes inactive. This is disabled. And whatever is your load line, that will get enabled. So whatever you are giving parallel input, it will go to here, and it will get into the XOR gate. So that is what we say here. The AND gate gets connected to the parallel inputs are enabled, and the AND gate connected to the Q outputs of the previous flip-flops are disabled. This is it is connected to the Q output of the previous flip-flop. So this gets disconnected. So this exactly takes only 1 clock cycle because we are giving it parallelly in. Next we have something when the shift is 1. Now that you have given the input, we need to do the shifting, right? So for that we will use the shift to be 1. So when shift is 1, this AND gates get enabled, and this load line will go off. That means this is disabled. Now input is disabled. So where is your input coming from? It is coming from the previous flip-flop. That is how this mode 2 works. So first we have parallel loading, then we have serial shifting. So the whole parallel loading takes 1 clock cycle. Here it takes 4 clock cycle because your data has to go through each of this, right? It will take 4 clock cycles to complete the whole process. So when you're writing here, we can see Here we have two conditions. Here you are writing also about load. See, if it is what happens is, if load line is enabled, whatever is your parallel input, that will go as an output. But if load line is also not enabled, your shift is 1. That means your main line shifting process is enabled. Here it will, you will get the same as your serial in parallel out and serial in serial out, what we saw same. Similarly, we'll see in this also. It will shift out. And you are connecting this temporary variable to serial output. So each one will come one by one. Then you have parallel in parallel out. This is the fastest one, and it is used only to for like a buffer to hold the data. Data is loaded all at once and read all at once. How it works? Since everything happens in parallel, it only takes one clock cycle for both input and output. Temporary data storage or buffer registers. So these PIPO shift registers are also called as buffer registers. It is like a multi-line highway where all cars enter their lines and exit their lines at the same time. So this is your parallel input, whatever you're seeing, you're giving it to each of these flip-flop. And at the parallelly, you are getting the output. So it takes only one clock cycle to complete the whole process. See, this is the fastest type of register because it does not actually shift data between stages. It acts like a multi-storage latch. It means it is holding it for a small amount of time and releasing it. See, used with the primary uses, it is used as a buffer or a temporary memory. It holds the data steady so that the rest of the circuit can process it without the input data changing midway. So this is very direct. You see the code only you can understand. If the reset is on, your output is 0, or else whatever is in your parallel input, that will be connected to the output. So you are giving input, that is only being shown as the output. So it acts like a D-latch. Same thing happens in D-latch, right? If you have any doubts, feel free to put it down in the comment section. Thank you.